Hello and welcome back. In this video we'll be starting section 7.4, which is on vectors. So a vector is essentially an arrow, and I think this is a pretty nice way to think about it. Arrows have, if I draw an arrow on the screen, it has a direction and a magnitude, which also means this is just a fancy word for size. So if we talk about different vectors, we're talking about different arrows with different sizes pointing in different directions. All of these are different vectors. Normally in mathematics we talk about numbers, and a number is what we're going to refer to as a scalar as opposed to a vector. So the difference between a vector and a scalar is that a scalar is just a number. It has a magnitude. You can talk about the size of a number, but a number itself doesn't necessarily have a direction. So in order to define what a vector is, we do need to say that it's pointing in a direction. So when we draw two vectors, we might want to know when they're equal, and two vectors are equal if they have the same direction and the same magnitude, the same size. So again, the only two things that you need to define a vector are what direction is pointing in and how long is it. What's the size of the vector? So as long as those two things are the same, you have the same vector. So we've got a few examples of vectors in here. We've got some that are pointing up and down, at other angles, across. So which of these vectors are going to be the same here? So here, this first vector, we have pointing straight up, and it's about as long as the gap between the two lines there. So we need another vector that's pointing straight up for it to be equal. So this one's pointing down. This one's also pointing. This one's pointing up. So, but the difference between this vector and this vector is that the first one's a lot longer than the second one. So they don't have the same magnitude. They don't have the same size. So they're not equal to one another. We have vectors pointing in other directions. Here's another vector that's pointing. Forgive my bad drawing, but it's pointing is about the same length and it's pointing straight up. I would consider those vectors to be equal to one another. If I had perfect drawing skills, it would be a lot easier to see. This one is pointing straight down; it's that length. But what we'll see is that there are no vectors in here that are also pointing down that are as long as the gap between two of these lines. Here I have a vector that's pointing straight down. Maybe I can use a different color. That's a little short vector, and this is another little short vector that's also pointing straight down. I don't think any of the rest of these are going to be equal to one another. So we've got vectors pointing down and to the left, up and to the left, down to the right, up and to the right. None of those are equal because none of them are pointing in the same direction. A vector pointing straight to the right. So this is so there's only those two pairs of vectors that are going to be equal in here. And we can refer to vectors in two different ways. The one nice way is to refer to them as the following. So if I have a vector, you can say where it starts, say the starting point, and you can say where it ends, the end point. This is also called the terminal point in some cases. But if it starts at O and ends at P, we can write OP, and we can even add a little arrow above it if we want to, or we could just refer to it as OP. And this means start at O, end at P. The other way that we can name a vector is we can give it a variable name. So in the same way that I could call, say, a number x, I could give a vector a name and just call it v. And the way that we denote that this is a vector and not a number is I draw a little arrow above it. Now, the thing is, when you are typing, quite often you don't have a key that says put an arrow above the letter. So in typeface, normally you would bold it. So if v is going to be this vector, I can't really draw bold, but you would just have a bold v, and that would be the same thing as when I'm writing, I could just put an arrow above it to say this is a vector and not a scalar. So So that'll just come up a little bit. We can name vectors, and there are a few things that we can do with vectors. So one is we can talk about the opposite of a vector, and the opposite of a vector we write as negative of that vector, and as you might expect, it's just going to be essentially the same vector pointing in the other direction. So here we have the vector v, which is pointing up and to the right. It's about that long. So if I draw the same vector but pointing down and to the left, the exact opposite direction, this is negative v. And that's all there is to a negative of a vector. It's the same vector, just pointing in the opposite direction. Here we have the vector x, so we'll draw the same vector, just pointing in the opposite direction, and that is going to be my vector negative x. So there's not a whole lot to the opposite of a vector. It's pretty straightforward. But we can think of this as -1 times a vector. So what about other numbers? So if we take a positive number and we take it times a vector, we're just going to lengthen or shorten that vector depending on what the number is, and it's going to be pointing in the same direction. So for instance, if I have my v here, so same as before, pointing up and to the right, and it's about this long, I can talk about 2v, and 2v is going to be the same vector. Oops, maybe I want it like this, and it's going to be twice as long as v. So again, v and 2v point in the same direction. I've just scaled up the vector 2 times the original length, and that's that's all there is to it. 1/3 v would be taking v and chopping it into about 1/3 of its original length. So this is 1/3 v. So multiplying a vector by a scalar, by a number, if it's a positive number, you're going to be pointing in the same direction, but we're just going to scale the length of it. It might be twice as long, might be 1/3 as long, and that's all there really is to it. If it's a negative number, we end up flipping it over, so that it's pointing in the exact opposite direction. So if I wanted, let me draw a little box here. If I wanted -1/3 v, well, I know here is 1/3 v, so then -1/3 v is just going to be pointing in the opposite direction. Again, if I started with v, I see, oh, negative, so pointing in the opposite direction, but 1/3 of the length. So with negative signs and with scalars, we'll just be, we know what direction it'll be pointing in, and we know how long the vectors will be. So if we can multiply vectors by numbers, the next step is going to be vector addition. And vector addition is something that is going to be the sort of the main theme of this section. So we've seen how to sort of draw a few vectors, see if vectors are the same, but also vector addition. If we want to add 2 vectors, and there are a couple ways to do this, but there's one way that's going to be more correct and more helpful. So I'll show you the ways that are maybe less helpful first. So here, if I want to take v plus u, we'll use the tip to tail method. And this is not the best method to use, but I think it's worth mentioning. So here is our vector v. It's pointing up and to the right, about that long. And here's our vector u. And the idea is that if we put them tip to tail, so again, v will start here and end here, and then we'll take u and we'll put a copy of it right at the end. V plus u is going to be the vector that starts at the beginning of v and ends at the end of u. Okay. So it's going to be, it'll be pointing somewhere in between v and u, and the length, this will actually be a little bit longer than both v and u. That's not always the case, but it is the case here, and I'll show you an example in a little bit of what can happen otherwise. We've taken v plus u. What about u plus v? So here, again, I'll start with u, and I'll draw u, so it's going to be pointing over, about like that. And then v is pointing up and to the right, about that long. Apologize for my sloppy drawing. And then u plus v is going to start at the beginning of u and end at the end of v. So this is going to be u plus v. And what you'll notice is that these two vectors, maybe I can draw that in red, the vector v plus u and the vector u plus v are in fact the same vector. It's maybe not obvious from my drawing, but u plus v is the same thing as v plus u. So just like with numbers, it doesn't matter the order in which you add vectors. 2 plus 3 is the same thing as 3 plus 2. U plus v is going to be the same thing as v plus u. Vector addition works a lot like numbers. And the one final way that I want to show you how to add vectors is more or less, it's what the book calls the correct way. And I think that this way is very, very helpful for a lot of reasons. Calling it the correct way, I think there's lots of ways to do this. But anyway, so v was the vector is pointing up and to the right, about that long. And u is the vector pointing straight to the right, about like that. And what we can do is we can actually create what's called a parallelogram. So I will make a copy of u up here, and I'll make a copy of v over here. And in fact, maybe let me do these in with dotted lines, so it's a little bit easier to see. So this up here is just another copy of u. It's pointing in the same direction, it has the same length, so we know that those vectors are equal. They just happen to be in different places. Over here, we have the vector v, and we have the vector v pointing up. And again, this is the same vector, they have the same length and the same direction. They just happen to be in different places. And from what we saw before, v plus u or u plus v, however you want to add them, starts at the beginning and ends after following both vectors. So here, if we start at the beginning and end at the end of both of those vectors, this is our v plus u. This is more or less the best way to do this because there's a lot of information here. We can see that we have two triangles here. So we've been studying triangles all semester. We can learn a lot about these vectors by studying these triangles and the angles that are showing up in here. So this is going to be the correct way, the best way, the most helpful way to draw. So let's do another quick example where we're going to subtract vectors instead. So again, when I take v minus u, this is going to be the same thing as v plus negative u. In the same way that if I'm taking 15 minus 8, it's the same thing as 15 plus negative 8. Okay? So we'll just turn all vector difference, as in like if I'm subtracting vectors, we'll just turn it into vector addition, but we'll use negative vectors. So here I have v, and here I have u, just like before. V is pointing up and to the right, u is pointing straight to the right. But if I want to add v and u together, I'm going to add v. Sorry, if I want to subtract u from v, I'm going to have v, and I want to add negative u. Well, negative u is pointing the opposite direction, so it's going to be pointing like this. So there is negative u. And again, we can draw our parallelogram. And v minus u is going to be pointing up here. So this is going to be v minus u. And this is going to be the difference. I've just drawn negative u rather than u and added them together. And just as a quick aside, this is called the resultant. Whenever you add vectors together, this is called the resultant, and it's just a fancy term for a sum.